So hello everyone, welcome back to the channel. Today we are going to solve the problem BST maximum difference. So you are given a binary search tree and a target value. You must find the maximum difference between the sum of node data from root to target and from target to child leaf node. Initially you are at the root node. If target node is not present, then return -1. So let's discuss the question. So here we are given the question. So what we have to do, we are given the target 30 and here is given as a BST. Okay. So what is the property of BST? As we know, for a given node, we have left smaller, all nodes are smaller, and all nodes are greater. Similarly, at this node, all nodes are smaller and all nodes are greater. So this is what we have the property of BST. We already know that. Now, what is we are given the BST. So we will take the use of BST, but later on. Let's understand what the question is saying. So we are given this BST. So we need to find first target is equal to 30. So the question is, let's find target is equal to 30 to 25. Then we go to 35. Then we have seen that here is target 30. Out of all these, I have found target is 30. So what is the total sum that we get from root to target, excluding target? So we don't have to consider this target. So it is 25 plus 35. So exclude this target. So it is equal to 60. Okay. So this sum is 60. Now, what we need to find? Now this sum is 60. Now this is our target 30. Now, from this 30 to every leaf node, we will go to every leaf node and we find their sum. So if we take this 30 and 32, also we will exclude 30. So it will be, so let's say this is something like configuration. Let's, okay. So this is, let's remove this and this will be 30. Okay. So what we do, like here the sum is from 30 to down, we will go this. So we will not consider 30, so 28 plus 27. This is the upper sum. Okay. And this is the lower sum. Lower sum is 28 plus 27, which is equals to 55. Now we have many lower sum because we can go to many leaf nodes. So here also we go, it will be 28 plus 29. It will be equal to 57. Okay. So now we not consider 30 as they said in the question. We have to exclude 30. Now similarly, for this leaf node, we have 32. This. So out of them, this is the lower sum. So we have to maximize the upper minus lower. Okay. We have to maximize the upper minus lower. Now tell me one thing, that if I want to maximize it, that means I have to get this upper as greater as possible. Okay. And I have to get this lower as smaller as possible. Okay. So this is fixed. Upper is only one. Why? Because we have only one path to reach root. Always. Always. So upper is always fixed. Now we have to minimize this lower. So we have to find minimum lower sum. It is 32. So we will subtract from 25 plus 35 is 57. It's 60. 60 minus 32 is equal to 28. So this is our answer. Okay. So I'm again repeating the question is just like we have to find the target. Until the target, we have to find the sum. Now, similarly, for every target, we have to find its from target to leaf node sum, excluding the target. So whichever sum is smaller from upper, we will subtract the smallest sum, smallest lower sum. This will be our answer. So how can we approach this question? Okay. So from the question, we can understand that we have two things. First, we have to find the target. Okay. Now, we can find the target in many ways. If we use a, like we can go here, no 20, no 15, no 20, no 25, no 30. Yes, it is found. So it is a target. Okay. But this is a binary tree approach. But we are given that we have BST. So we will use this property. How? We will say it is 25 and we have to find target 30. So obviously it will have all childs smaller. So that means 30 will never be found here. Okay. So I will go here. So we will go to right of this node. Now we have find 35. So 35 is greater. So obviously it will have greater sum here, 45, 48, 50, 37, anything. But obviously these all things will be smaller than 35. So we will go down. Now we have found 30. So this is our target. So in this way, we will find target node. So this is something like searching in BST as we do searching in BST. So it is normal searching in BST. Now, what is the second thing we are going to do? The second thing we are going to do that we will start from this 30 and we'll find all the leaf sum. And whichever leaf sum is smallest, we will subtract it. So whenever we traverse, whenever we find this searching, so 25 plus 35, we will get 60. Okay. Now, this is the upper sum. This is the upper sum. Now from this 30, we will go downward and take all the sum. And whichever sum is smallest, we will subtract from this upper sum. Okay. So upper sum minus lower sum will be greatest only when this lower is more smaller. Because let's say I am taking 5 minus 2. And if I decrease this 5 minus 1, it will be 3, it will be 4. It is greater now because we are subtracting smaller number. So this is the intuition why I am subtracting the lower number. Okay. So now one thing that I want to clear now, as I made some summation in GFG, so I have seen they are not so they are considering target node as separate and leaf node as separate. So for example, I want to give, let's say here is the, but let's say my target is 45, and let's say I have no child here. Okay. And let's say I have 35, 36, like this is here. Okay. I have, since it is BST, so we have to consider something greater, like this is 47, this is 46, and something like that. Okay. So this is target. Now I try to find the sum here. Now obviously I will exclude this sum. So here sum is equals to 0. So what I will see, yes, it is smallest sum. So I will subtract this from upper sum. Upper sum. So that will become upper sum. It will be greatest. Because if I will subtract this, let's say above sum is 108. Okay, from root to 45. Above sum is 108. So I will subtract 108 minus this sum. So this will be the sum. But this sum is greater. So we will get smaller sum. But this sum is smaller because sum is equals to 0. We will take this. But GFG has not allowed this. We have we don't have to consider the null nodes. That means um, whenever under the target, we get some null nodes, let's say left and right. So we don't have to consider them. Okay. So this is the approach. Like what? So let's code the question. So here first, our first step is to find the target. So here we first find the target, and here we first find the upper sum. Okay. So here I create a function which will return the target root, and here we pass the root target, and here we pass the upper sum variable, which will be passed by reference. So that whenever we get the sum, it will be returned and we get the upper sum as it is. Okay. So now node star, we will create a function node star root int target and int upper sum. But okay. So we will pass it by reference so that whenever I get it, I will not remove it from here. Now, because when I backtrack, then the sum will be reduced. I don't want that. It should be added. And also we know that BST is one directional. So we don't have to traverse many directions. So that's why we are sure that whenever we get the sum, we will return there as it is. So if root equal to null, return null. Okay. And if root data is equal to target, we will return the root as it is because we have got the root data. If root data is greater than target, what will we return? We will return root left. Why? Because whatever root we have is greater, so we have to go to left, obviously. As we have done BST, target, upper sum plus root data. Or we can do here itself, upper sum plus is equals to root data. So we don't have to do it here. Now if root data is less than target, we will return root right and target and then upper sum. Obviously we have added. Now we will return none if nothing is found. Obviously we are adding it just for completing the function. Now we have found the target root. If target root is not found, if target root is not found, we will return minus. Now, if target root is found, so let's find the lower sum. Okay. So how can we find this lower sum? So as I said, we have to minimize the lower sum. So let's create the mini variable, which will be set to max variable in initially, and we'll find the minimum sum. Target root, pass the target root, minimum and 0. So we will create this min sum function and notice the root int ampersand mini, so that it is passed by reference. And here we will add this sum. Now this is the lower sum. Okay. Now what I have to do, I will traverse to every root. Okay. So as I said, if root left is equal to null, if root right is equal to null, we have to consider the lower sum. We add this lower sum because at last number is, this is the last node which is available before the leaf node. So we'll add this and just what we will do, and we will take the minimum is equals to minimum of mini comma lower sum, and we will return as it is. But if root is equals to null, as I said, if down the target root is available, just we have to return as it is. We don't have to consider. So this case will arise whenever the root node is just null node is just down of the target. Okay. Now we will go to left as it is, root left. Now we will do lower sum plus is equals to root data because we have to pass ahead. We are adding again and again, and minimum sum root right mini comma lower sum as it is. So we are getting root left, root right, and this is all about this. And then what we'll do, we can return here or not. We can go ahead. It's our choice also. And now what I will do, I will, because whenever I was finding this sum, so this sum will be from here. it will be adding 30. Similarly, it will be adding 30. Similarly, it will be adding 30. So we have to not consider this sum. So for that, we will subtract the target from the minimum. And then what we will return? Whatever is the upper sum minus the minimum. So that will be our answer. So let's compile it in the code. So let's submit the code. Yes, so it's totally working fine. So the two-step process, find the target in upper sum, find the lower sum, subtract the upper sum, but minimum because lower sum will have target available. So we have to subtract it and we have to upper sum minus minimum, we have to maximize the difference if minimum is smaller. So obviously this difference will be greater. And we don't have to consider root node because the test cases are designed in the GFG such that target node is separate, leaf node should be separate. If it is not present, so don't consider that test case. So this was all about the question. Thank you and have a nice